My dear friends, we are coming to a little difficult task in transmission line protection using overcurrent and earth fault relays. Till date, we had been talking about a source on one side and load on the other. Now, on all buses there are loads and on all buses there are sources. The system in any state, any nation is like that only. It is an interconnected system, 7 bus system, 11 bus system, like that. There are many transmission lines. And in earlier case you were seeing that one relay is backed up by either 1 or 2 relays. Here one relay will be backed up by about 10 or 11 relays also. Therefore, the setting of overcurrent and earth fault relays becomes very cumbersome, and you cannot do it manually using scientific calculator. You have to use the computer and you have to design the algorithm. Therefore, usually for 132 kV to 20 kV and onwards, overcurrent relays are not used as main protection. However, they are used as backup, but not main. Distance protection or line differential protection is used as main protection. But however, we will see. You see, in this case, it is also difficult because you see there may be certain fault for which the primary relay may not also operate and the secondary relay may not also operate. Some third relay may operate, and that is known as sympathy trip. That becomes very difficult. Sympathy trip means the wall operations will be there, cascaded tripping can also occur. Therefore, researchers are trying to reduce the sympathy trip, but yet sympathy trip has not been removed as on date. So if we go further, you see, in this coordination, main point is if you want to calculate the plug setting, you have to take one relay. You see, in the earlier case, you are taking the relay towards load. Here there is no relay towards load. So you will have to take any relay at random, right? And you will have to run the power flow analysis under no fault condition. And you will have to run the power flow analysis not only for one case, for many cases. If there are 50 lines, all 50 lines are on, and what is P plus JQ in all the lines. Now one line is off, number 1, then what is the power? Line number 2 is off, 1 is on. Line 3 is on, others are, line 3 is off, others are on. Like that, you will have to run 50 power flow analysis by different methods, Gauss-Seidel and Newton-Raphson or whatever you are using, fast decoupled method. Many methods are used, and you run that method, and the maximum current through R1 will decide the plug setting of R1. So very cumbersome, right? So this is the way in which the plug setting is done. For time setting, you will have to do fault current calculation. Like that, similarly, you will have to do fault current calculation for different contingencies, line contingencies. And as far as I know, people have yet worked on one line contingency. 2 line contingency means 2 lines at a time are off. That has not been yet done in research world. I do not consider myself to be a researcher. I am a consultant. I am an industrialist. I can solve the industry problems. I am not a researcher. I cannot invent. But as far as I know, as far as my knowledge reaches, nobody has yet done work on double line contingency. Anyway, so you will have to run the fault current calculations. Then more important is primary backup pairs, because you see one relay is backed up by 11 relays or 12 relays or 13 relays. If you forget one relay, then there will be a problem. So for primary backup pairs also you have to run a program. Actually the network you will have to feed to the computer. How you will feed the network? For feeding the network there is a uh, uh, algorithm which is known as link net structure, which is working on three vectors: list, next and far. I am not going into the details of that because it is too much of detailing, and the normally application engineers do not need this. But based on this, you see, the primary backup pairs are found. Then you have to calculate the plug setting and time setting by different algorithms. So this is the way in which you have to go when you go for that. So we will take one example. That example will let you know how difficult and how complicated it is. The system is very simple because we cannot take very system with 3 buses, 4 buses or 7 buses. We have taken the system with 2 buses only. I read out figure 7.29 shows a single line diagram of a simple interconnected power system network. Relays R1 to R4 are directional normal inverse overcurrent relays wired for 3 overcurrent and 1 earth fault relays. Overcurrent unit ranges 50 to 200% of 1 ampere, ground 10 to 40%, and relays R1 to R4 are voltage controlled overcurrent relays such that their PS will reduce to 40% automatically if the voltage is less than 70%. You see, that is the requirement here. Fault currents for faults at F1 and F2 are given. So we go further. This is the system. Very simple system. But and it is also given that the auxiliaries consume 10% because it is 210 megawatt, it does not give to consumer. 10% it takes away. The student boiler, feed pump, primary air fan, the secondary air fan, it has to run the induced draft fan, forced draft fan. So it has to do many things, many coal mill is there, crushers are there. So all these things will consume power. So 10% of power is consumed, remnant power is available. So if you think about R1, how you will decide the plug setting? One line contingency means lower line is not available. And then how much power will flow through R1? Obviously it is here very clear that if load is less and generation is more, then the load will be, the plug setting will be decided on load. But if generation is less, then the plug setting will be decided based on generation. So accordingly, before that, this fault current calculation, which has to be done, that I have done for you, I have done manually on scientific calculator because it is a small network, otherwise it is not possible. So for F1, see F1, when the fault occurs at F1, through CT1 maximum current passes and through other CTs low current passes. Similarly for F2 and similarly for line 2 ground fault. The fault currents are given to calculate these things. So now what is the solution? We have to find out the plug setting. Now there is no last relay, so we will take one relay, say R1, and R1 we assume TMS 0.1. You can assume 0.05 also. I am assuming 0.1. So what is the plug setting? Plug setting is your power is 567 and your load is 600 megawatt. So obviously the plug setting will be decided based on 567, which is coming out to be 116.7%, that is 125%. Similarly, PS of R3, R4, here the ratio is 1500 bar 1 for R1, R2. For R3, R4, you can check up the ratio. R3, R4 is 100 bar 1. Ratio for R3, R4 is 100. 1000 bar 1, sorry. 1000 bar 1. So, the R3, R4, the load is less, generation is more. So, we decide based on load, and that also comes out to be 125%. Primary backup pairs, here it is very easy to find out, you see, not difficult. Therefore, I'm just giving you R1 is backing up R4, but R4 is backing up R1. Very stringent. R2 is backing up R3 and R3 is backing up R2. There are 4 primary backup pairs. Based on this, if we go ahead, R1 and R4 give backup to each other. So we first find out the time of operation of R1. For phase relays, you see, for phase relays, what is the time of operation? For phase relays, the currents are given. What are the 6852? 6852. So 6852, 6852, 6852 divided by 125% of 1500 is a C ratio 0.4, because the plug setting reduces to 0.4 times because fault has occurred. 9.136 is PSM. Time of operation log 10 PSM 0.3123. Therefore, the top of R4 is 0.25 more, 0.5623. So, lookingly, R1 is 0.1, so R2 is also 0.1 because the system is symmetrical. R4 is 0.1, so R3 is also 0.1. That is what is felt, right? That is what is felt. But that is not true. We will have to take the fault at F2 and prove that yet the discrimination time margin is 0.25. So, for fault at F2, the R4 fault is 5539. So, PSM is 11.078. So, time of operation is 0.2872. Say, TMS is 0.1. I have not changed. I cannot change either PS or TMS. PSM of R1 also I have not changed. 1910, 1.25, 0.4 because it reduces by 0.4 times. 0.7379 second is the time of operation. The discrimination time margin available is 0.4507, which is more than 0.25. So just at one go, I could complete the example. It could have happened that this would have been less than 0.25. That means top of R1 minus top of R4 is less than 2.25. So obviously you will have to increase the top of R1. For increasing the top of R1, you will have to increase instead of 0.1, 0.15. And if you change 0.15, so R4 will also change. Then once again you do. So it may happen that after 9 or 10 iterations you come to a final setting. Fortunately here, by one go, we have decided the settings R1, R2, R3, R4 125%, R1, R2, R3, R4 TMS is 0.1. That is what we could do. So this was, by the way, simple, but otherwise it would have become difficult. So my friends, please stay tuned with Adapt.me. Let the name of the this app Adapt.me rise in the sky. It is not in my hand. I cannot do alone anything. My all learned and loving audience will be able to do it. They have to read the videos fully, then I will earn watch hours. You have to send it to 100 or 150 electrical engineers who would read this, then I will earn the watch hours. You see, you are getting the material free of cost. You don't pay me in terms of money, but you pay me in terms of hearing this video, and YouTube pays. So YouTube will pay. But for that, I have to have millions and billions of view hours. First milestone is 4,000 view hours. I am waiting very eagerly to see that by 15th July, my first milestone, 44,000 watch hours come, and that is up to you, my dear friends. you have to do it. You can do it. I cannot do it. So I very earnestly request that please watch the videos fully, and please ask your friends to watch the videos fully, and I can assure you that you will get a lump of knowledge which you would not have got at universities, and you will be able to solve many problems in your industries if you read through these videos. So my friends, with these remarks, thank you so much and good day.